this video, we're going to look at the Kinetic Molecular Theory, sometimes called KMT, and what it means to be an ideal gas. So the Kinetic Molecular Theory is a theory that explains why ideal gases behave as they do. Like, what does it mean to be an ideal gas? What conditions or what rules do you have to follow in order to qualify a gas as an ideal gas? So there are 5 assumptions, and the AP does expect you to know these 5 assumptions for this Kinetic Molecular Theory, sometimes called KMT for short. So the first is that an ideal gas is composed of many tiny particles, and they're traveling in random straight line motion. That makes sense that your gases are moving randomly in the container, and if you have a mixture, these particles are moving independently of one another. 2, the volume of the gas particles is negligible compared to the total volume of the container. What does that mean? That means that the gas particles themselves are so small and so spread out that if I were to take all of those particles and put them right next to each other, the volume that they would take up is so negligible compared to the entire volume of the container. So this is kind of showing that your gases are very spread out, and this is why when we're doing PV-nRT calculations, we're using the volume of the container that they're in, since your gases expand and compress to fill the container uniformly that they are in. 3, the attractive and repulsive forces between the particles are negligible. So ideal gases do not attract each other and they do not repel each other. Again, they behave independently of one another, even if you have 2 gases in the same container. 4, collisions are perfectly elastic, meaning that the total kinetic energy of the gas before and after a collision is the same. So when you collide, yes, some particles might lose some energy and some particles might gain some energy, but the total kinetic energy of your sample is still the same. So that's why we say perfectly elastic. And 5, the average kinetic energy is directly proportional to the absolute temperature of the gas. And that's something that we've already talked about, the definition of temperature being average kinetic energy, and just make sure that we are talking about the absolute scale, meaning the Kelvin scale. So if your gas follows these 5 rules, then they are considered to be an ideal gas, and you can use the ideal gas law. Now, gases that we encounter every day might not exactly fit these assumptions. The gases we encounter every day, a lot of times we call them real gases. They might not exactly fit this theory, and therefore, if you plug into PV-nRT, there might be some calculations that give you a little source of error, and we'll talk about that later. Okay, so you should be able to, knowing your ideal gas law, be able to think about the relationships between the different variables. If something's directly proportional, feel comfortable drawing a graph. A directly proportional graph should look something like this. If x goes up, y goes up in the same degree. So if x doubles, y doubles. Inversely proportional would have a graph looking like this. As x goes up, y is very small. Y goes down. So if x were to double, y would half. Okay, so you should also be able to kind of logically think about these relationships, and you can think of it logically. If you're more comfortable looking at the equation and figuring it out that way, that's totally fine, and I'll talk about the 2 different ways. So let's consider pressure versus moles and molecules. So here's 2 different containers. I'm keeping temperature the same. I'm keeping the volume of the containers the same. Anytime you have a rigid container, the volume would be the same. So if you ever approach a problem and they say something about there being a rigid tank or the container is staying the same, the volume would stay the same. So in this situation, volume's the same, temperature is the same. The only difference is this has more moles or more molecules of gas than this first container. So in this container, I have more moles. So if I have more moles of gas and more particles, and these are going to collide with each other more often. Not only will they collide with each other more often, they're going to collide with the walls of the container. And what did I say collisions with the walls of the container is kind of interpreted as? Pressure, because you're going to have more force per unit area on that wall. So pressure would go up. So as moles goes up, pressure goes up. That is a direct relationship. If I were to draw a graph of pressure versus moles or vice versa, I would get a directly proportional plot. And so you can think of this logically like we just did, thinking of visualizing these diagrams. And a lot of times the AP likes to draw particle diagrams, so that's a nice thing to think about. But you can also just look at the equation, the ideal gas law. Sometimes it's helpful to look at it with the way with the 1s and the 2s that you get by setting PV-nRT, rearranging it to equal R. But if I were to hold temperature and volume constant, okay, and then if pressure were to double, moles would have to double. Pressure goes up, moles goes up. That would be directly proportional. So you can also just think of these relationships mathematically. Let's talk about volume and pressure, and let's hold temperature and moles constant. So these are two different containers. One is smaller than the other. The volume has gone down, but they have the same number of molecules and thus the same moles, and temperature is held constant. So this one has a smaller volume, okay? So there would be more collisions with the walls of the container, right? Because the space has decreased. So that means that the pressure would go up, because that's what we said, the more collisions with the walls of the container, the more pressure. So therefore, volume goes down and pressure goes up. That's an inverse relationship. And if you were to do a graph of pressure and volume, you would get something like this. So we can think about that logically. We can also look at our equation, whether you want to look at PV and RT or the ones with 1s and 2s, either way is fine. But if moles and temperature are constant, if volume were to go down, pressure would have to go up, and vice versa. So that's an inversely proportional relationship. Okay, let's think of another relationship logically. So here's two containers of the same volume. You have the same number of molecules, so you have the same moles, and all I've done is I've increased the temperature. Well, what is temperature? Temperature is average kinetic energy, or energy of motion. So what's happening to the speed of your particles? They're moving faster. If they're moving faster, what's happening to the number of collisions with the walls of the container? The collisions is going up, so what's happening to the pressure? The pressure increases. So when temperature goes up, pressure goes up. That is a directly proportional relationship. And if I were to do a graph of pressure and temperature, I'd get a graph that looks like this. And again, you could think of that logically, or you can go to your equation for volume and moles being constant. If pressure were to double, temperature would also have to double, so that the fraction P over T stays constant. And these were kind of all those other rules of those different scientists that I said you didn't really have to memorize. You can derive it from the ideal gas law, but you should also be able to think of it conceptually and logically like we just did here. Okay, take a moment and try this. Sketch a graph of these things. Figure out if these are directly proportional, inversely proportional, and draw a graph. Take a moment and then check your answer. Okay, pressure versus volume, these are inversely proportional. And again, showing you that I could just figure this out by looking at the equation PV and RT if you want. I'm going to look at this equation instead of the one with the 1s and the 2s. Okay, if moles and temperature are constant, then I can group them all together with the R into a new constant and just say K. PV equals K. That's where that came from Boyle's law. So if pressure goes up, volume would have to go down, and vice versa, so that it's equal to this. These two things multiplied together is equal to a constant. So this is an inverse relationship. I didn't draw the graph here, but make sure you go back to your slides so you can see what the inverse relationship would look like. Volume and temperature at constant pressure and moles. Okay, so if pressure and moles were constant, okay, I'm going to group them together with the R, and it's going to turn it into some other constant that's not R anymore. But I could look at the relationship like this. If volume were to go up, temperature would also have to go up, so that I'm equal to this constant K. And that would be a direct relationship. Make sure you look at what the direct relationship graph should look like. Volume versus moles, same thing. I can group everything held constant with the R into what's called a K, a constant, and I see that same directly proportional relationship. Notice if variables are on the same side of the equation, like P and V, or like N and T would be, you're going to have an inverse relationship. If variables happen to be on the opposite sides of the equation, then you're going to have a direct relationship like P and T, or V and T, or P and V and N. Those are going to be direct relationships, because also if you move them to the other side of the equation, it's like they're going to be one in the numerator and one in the denominator equal to a constant. Take a moment, try this problem, and then check your work. So this is a great kind of conceptual problem, ones that you might see on your test or on the AP exam. It's known that two balloons at the same pressure and temperature have this volume relationship. The volume of the Ne balloon is 2 times the volume of the argon balloon. Which of the following best represents the mass ratio? So sometimes you see problems with balloons in them because balloons have variable volumes, right? The more moles of gas you have in there, the bigger the volume would be. The volume is not a rigid container, which would always be the same throughout the course of an experiment or anything like that. So sometimes you see balloons because if you see a balloon, you could assume the volume not fixed. So here they do tell me that the volume is 2 times that of argons for neon. So notice this is same temperature and pressure. So I know that volume and moles are directly proportional. So whatever the relationship with volumes is going to be true of the relationship with moles. The moles of neon is going to be twice that of the moles of argon. Now some people don't really like looking at variables like this in an equation. So just make any type of assumption. Let's assume that argon is going to have 1 mole in it. Let's figure out how many moles of neon there would be. There would be double it, so there would be 2 moles of neon. Okay, well now let's change this into masses. So because they're asking about the mass ratio, not the mole ratio. If they asked about the mole ratio, I would say it's like a 1 to 2 and we'd be done. But they're asking about the mass ratio. So if neon has 1 mole, so if argon has 1 mole, and look up the molar mass, that's 40 grams of argon. If neon has 2 moles, okay, the molar mass of neon is 20, then there's also 40 grams of neon. So that's actually a 1-to-1 mass ratio. So just because you have different mole amounts, remember that doesn't translate to the same mass ratio. You have to look at the molar mass there. And the AP loves to throw tricks with that. Instead of giving you mole amounts, they give you mass amounts, and you have to mole that out. Or like here, instead of thinking of the mole relationship, you have to go a step further and think about how that affects the mass. Take a moment, try this problem, and then check your work. Okay, so it tells you have a sample of nitrogen gas and it's fitted with a piston. What a piston does, it is essentially allows a pressure to be maintained and it allows the volume to shift so that your volume can change based on how many moles of gas you have and so on and so forth and the conditions that you're at. So basically a piston cylinder device maintains a pressure. So it's fitted with a piston that maintains a pressure. So anything about pressure changing, I definitely don't want to pick because it says right here, maintains a pressure. The gas is at 45 degrees Celsius and your volume is at 6, and then you cool the gas. Okay, temperature's going down. What's happening to volume? Volume's also going to go down because you have a directly proportional relationship between volume and temperature. So you really have to know those relationships, whether you want to memorize them or derive them on the spot, think of it logically, look at the equation, however you want to do it, but you've got to know those relationships because you're going to see a lot of conceptual questions about that. Okay. The other thing that you're going to see is we're going to go a little bit further with kinetic energy. So there is an equation that relates kinetic energy and speed. So there's this equation, if you've taken physics before, you might have seen it. Kinetic energy is 1/2 mass times velocity squared. Okay, so m is the mass of your gas particle, v is your velocity. So there, very, very rarely have I ever seen them ask on the AP for you to actually plug in and calculate a number. But you do need to know 2 different takeaways from this equation. The takeaway number 1, the higher the temperature, think about what we define temperature as. The higher the kinetic energy. So if I'm looking at this equation, the higher the kinetic energy, what about your speed? The higher the speed, or the faster the particles are going to move, the higher the velocity. Okay, so that's the first takeaway. If you increase the temperature, your particles are going to move faster. The velocity is going to increase, and that makes sense. Okay. Takeaway number 2. Okay, so if we're talking about the same conditions of temperature, okay, all gases are going to have the same average kinetic energy. And we say average kinetic energy because some particles might be moving faster and some might move slower, but on average we have this average kinetic energy. So anytime you have the same temperature, you have the same kinetic energy. For a given temperature, though, if you have more mass, okay, so same kinetic energy, if mass were to go up, what's going to happen to the velocity or the speed? The speed is going to go down, okay? So at the same temperature, small molecules are going to move faster than large molecules. So even if I have 2 gases at the same temperature, they are not going to move at the same speed. Whichever one is lighter, whichever one has the lower molar mass is going to travel faster. So for instance, if I'm looking at CO2 and O2, and they're at STP, so they're at the same temperature, they have the same average kinetic energy, which one would travel faster? O2 would travel faster because it has a molar mass of 32. CO2 has a molar mass of 44, so O2 is lighter, it would move faster. Okay, and just logically that also kind of makes sense. So you should also be able to look at what's called a Maxwell-Boltzmann distribution curve. And this is a distribution curve. It shows the distribution of speeds or kinetic energy throughout the sample. So if you notice, your y-axis says either fraction of molecules, or sometimes it might say number of molecules, and that's your y-axis, and your x-axis says speed or kinetic energy. So what this is showing is that in any sample, you're going to have particles traveling around an average speed, but you're going to have some particles traveling a lot slower. You're going to have some particles moving a bit faster, and it kind of looks like this bell curve. Okay, so what's going to happen to this curve if I change the temperature of the sample? If I change the temperature of the sample, more molecules are going to be moving faster. So I'm going to expect this curve to shift to the right. And what actually happens that they've seen and that they've measured via experiment is that not only does the curve move to the right because the average speed increases, but it also flattens out. So the average speed increases as temperature increases. That's why it's moving to the right here. But also the range of speeds widens. More molecules are traveling at an even faster speed. That means, yeah, some molecules are traveling at a slower speed than the average too. But notice that where this curve ends is so much further to the right. Okay, the area under the curve should be exactly the same because you have the same number of particles in your sample, so that hasn't changed. But on average, because the temperature goes up, the particles are traveling faster on average, and even more particles are traveling at an even faster speed. Okay, the range widens. So it moves to the right and it flattens out, as you see here. Okay, as you see here. The other effect is molar mass. So we said those were kind of the two takeaways from that average kinetic energy equation. We said, okay, temperature is going to have an effect on speed because temperature affects average kinetic energy, and molar mass is going to have an effect on speed. The lighter particles are going to move faster. So even at the same temperature, okay, if I were to plot the different samples containing, let's say, the same number of moles, the same temperature, these particles, notice that H2, which has a much lighter molar mass or smaller molar mass than O2, notice it's shifted to the right. And it's also flattened a lot. So just as you saw with temperature, the average speed increases as molar mass decreases. Lighter particles can move faster. The spread of speeds narrows as you get to higher molar masses. The spread of speed widens as molar mass decreases. Okay. And it makes sense that it narrows as the molar mass increases because more particles are traveling at an even slower speed as well. The total area under the curve is constant. So here are your takeaways. Not all molecules in the same sample have the same speed or energy. Some travel very fast, some travel very slow, some change speed when colliding, but the total kinetic energy is constant. 2, a higher temperature sample has a higher speed, as we would expect, and thus a higher kinetic energy, because we know kinetic energy is 1/2 mv squared. So a higher temperature will shift the curve to the right, and it will flatten the curve. The total area under the curve will be the same as the number of particles has not changed. For the same temperature, a sample with a lower molar mass will have a higher speed, and it will shift the curve in the same way described above. So this is really the same kind of conceptual content that we looked at with the K equals 1/2 mv squared, but shown graphically. And you know that the AP loves to show graphs and charts and things like that, picturesque. So it's good to be able to interpret this Maxwell-Boltzmann distribution curve too. So make sure you know this curve, know the axes, know what's the y and what's the x, be able to sketch a plot, be able to show the effect of a temperature change or a change in molar mass, and make sure you're able to explain why these changes affect the speed on a molecular level. You could even reference that K equals 1/2 mv squared equation. Take a moment, try this example. Label each curve with the appropriate gas. Okay, so notice that this one is the most narrow and has the lowest average speed. This one's the widest with the highest average speed. So this one must have the lowest molar mass, okay, and this one must have the highest molar mass. So this would be Xe, this would be a bit bigger, this would be argon, this would be neon, and this would be helium. So as molar mass decreases, my speed increases. Okay, let's take a look at this. Label each curve with the appropriate temperature. All right, so notice that 200 is the lowest temperature, 800 is the highest. The highest temperature would have the highest average velocity, so and this would have the lowest average velocity. So this would be 200, this would be 400, and this would be 800. Notice as temperature increases, the plot moves to the right and it flattens out. The total area under the curve would be the same because you have the same velocity. Take a moment, try this example, and then check your work. Here's a curve at 273 Kelvin. What would the curve look like at 1273? And again, yours might look slightly different, but I'm just looking for a shift to the right and it flattening out. And if I increase the temperature again, another shift to the right and a flattening out. Notice my y-axis is number of particles, my x-axis is velocity. Sometimes it might even say kinetic energy. Take a moment, try this conceptual example, and then check your work. These two containers, they're rigid containers that are both 2 liters. They have the same temperature and the same pressure, but the only difference is they are 2 different gases. This is H2, this is N2. So what's the same and what's different? Moles of gas. Well, if I have the same volume, temperature, pressure, and I plug into PV and RT, I'd get the same moles. So that would be the same. And if I have the same moles, then I have the same number of molecules because there's 6.022 times 10 to the 23rd molecules in a mole. If they're at the same temperature, they have the same kinetic energy. Anytime you're at the same temperature, you have the same kinetic energy. So if you ever see a question about kinetic energy, all you're looking at is temperature. Temperature is the average kinetic energy. Okay, here's where this will be different. Molecular speed. Just because they have the same average kinetic energy, that's not the only factor that affects speed. The molar mass affects the speed, and they have different molar masses. So they're going to be different. Which one's going to move faster? H2 gas would move faster, N2 gas would move slower because N2 is heavier than H2. Density. This is where that equation PM equals DRT, PMDIRT, comes into play. Okay, they have the same temperatures, they have the same R, but there is a molar mass in that equation. PMDIRT, PM, M is molar mass, equals DRT. As the molar mass goes up, the density goes up. N2 has a higher molar mass, so it would have a higher density, and it makes more sense. Okay. Another concept is diffusion and effusion. It's very similar to the speed of the molecules, but it just refers to what the molecules are doing while they're moving. So essentially, diffusion is the process of a gas spreading out to fill its container. So this is like if you spray perfume in a room and eventually you smell it across the room, it's because the gas moves throughout the room to eventually fill the container uniformly. We call that diffusing, or diffusion would be the noun. Effusion is when a particle escapes through a hole in a membrane. So like a balloon deflating is effusion, and the verb of that is effuse. Just like we said how smaller particles are going to move faster, smaller particles are going to diffuse and effuse faster than large ones. Take a moment, try these conceptual examples, and then check your work. Which of the following gases would effuse at the fastest rate? So I'm looking at the molar masses here. Okay, so I notice that this has the lowest molar mass, so it will effuse and diffuse and just travel in general at a fastest rate. Which two gases would diffuse at nearly the same rate? So I'm looking at what has the same molar mass. So I would say these two would be relatively similar because they have similar molar masses. Xe gas would diffuse at the fastest at, so now I'm just varying the temperature. The higher the temperature, the faster the speed. Just make sure that you're comparing your temperatures in the same units. So this would be 293 K, this would have the highest temperature, and therefore the highest average kinetic energy, and therefore it would move the fastest. you can actually calculate just how much faster something's going to effuse or diffuse than something else with an equation called Graham's law. And R1 is the rate of effusion for your first gas, R2 is the rate of effusion for your second gas, and it's equal to the square root of the molar masses. Notice that whatever's in the numerator here in my rate, it's in the denominator here in my equation. And feel free to go to the textbook to see how this is derived. I just didn't want to waste time. But a lot of times you're solving for this fraction, R1 over R2. How much faster does one thing diffuse or effuse from another? So let's look at an example. How much faster is HE gas effuse compared to N2? So I'm looking at this Graham's equation. It's not in your formula sheet. Very rarely do they ask you to calculate it, but it is something you should probably know in case they do ask, or in case they ask conceptual questions. So it's one other, aside from PIMDR, that you might want to memorize. So I like to fill in my subscripts with which elements they're talking about or compounds they're talking about so that I can make sure I'm putting everything in the right place. They want to know how much faster HE diffuses compared to N2, so I'm going to put HE on top here, N2 here, and switch the molar masses in the fraction here. So if I plug it in, 28 over 4, take the square root, I get 2.6. Now, what does this number mean? It means that helium diffuses or effuses 2.6 times faster than nitrogen gas. Does that make sense? Absolutely. Helium's lighter and it should move faster. So you should always make sure that your answer makes sense. So notice that I'm solving for the fraction here, 2.6. If the thing that moves slower is on top, you're going to get a number less than 1. If the thing that moves faster is on top, you're going to get a number greater than 1. And that makes sense.